Okay, so what I have up on the big screen, take a look. This isn't in the lecture notes. This is just a little simulation I built last night. This is a bunch of resistors. It's got some wires in it too. What do you notice about the numbers versus the speed of the charges? All right, so if I point up, let's point at some specific ones. Can you guys read that number?
9.
That's 9, and this is 0. This is 9 to 3.2, 3.2, 3.2, 3.2. Why are these all the same? Why are these all at 3.2 volts across the top?
All in the left.
They're all they're connected. All right, so why does the current appear to be getting less and less? Because some of the current's going down here, then some of the current's going down here, then some of the current's going down here, and some of the current's going down here. These currents, these three currents, technically should all, well, maybe not all be the same. How come? Why aren't they all the same?
Because they're adding up and splitting up.
These, I will tell you, these are all the same resistance.
There's a resistor on the bottom side too.
These are all 10 ohm resistances. So if the high sides are all the same voltage and the 10 ohm resistances are all the same resistance, why is this current less than this current?
Chargers are lazy. They want to go to the quickest way.
Wrong. Wrong. Take a look. What does current flow depend on through a resistor? Does it depend on the voltage on the high side?
No.
Not really. What does it depend on?
Oh, wow.
The voltage across, right? So if you look at the first resistor, how much voltage is there from one side to the other? What's the voltage across this one? That's 3.2 volts. But if you look at this one over here,
It's only 0.3.
that's only 0.3 volts. So it's going to have way less current going through it. You see that?
Isn't there less volts because there was less current, not vice versa?
Ah ha 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 ha. Chicken or egg?
Yeah.
Chicken or egg. They're simultaneous equations, and I would argue that the reason that current flows is because an electric field pushes it. Wouldn't you agree? How do you create an electric field? With a voltage difference from one side to the other. The reason current flows is because there is a voltage difference. If you think of it that way, you will do much, much better in the circuits unit. Got it? Think of it as the voltage difference, the high side to the low side, is what's causing the current to flow, not the other way around.
So voltage difference.
That's why I have a problem with that V equals IR equation, which seems to imply that the voltage difference is caused by current flowing. All right? That's kind of a backward way of thinking about it. The reason we write V equals IR is because we don't like writing divide by symbols. Yes?
So for electrons to move, there always has to be an electric field pushing it?
Yeah, if you gotta, in order to get charges to flow, there has to be an electric field, right?
Well, how come like on the wire where there's no resistors?
Ah ha ha, up here. So why is there a current flowing here? Because I didn't show you all the decimal places.
What?
It turns out this is like 3.2000001, and this one is like 3.1999998. They both round to 3.2, but in real life, this wire actually does have a very tiny bit of resistance to it. Well, how much, if it's got a tiny resistance, how much voltage difference does there need to be to give you a current?
Very small.
Very, very small voltage difference is required to give you that current if the resistance is tiny. It's an interesting thing happens if you call this resistance 0, because what does the voltage difference need to be in order to give you,
Infinity.
right? A 0 voltage difference, right? So weird things happen, infinities and zeros happen if you call this resistance actually 0. So I didn't call the resistance of the wire 0. I called the resistance of the wire 0.0001 ohms. And that's what gives us this nice neat looking thing. It's just because you rounded it off that you don't see the extra decimal places. Does that make sense? So, yeah. So this is kind of an important idea going on here. It's like I made this thing just to test to see if the circuit builder actually works, but it's actually really good for this class because you can actually see in every single case the charges always flow from high voltage to low voltage. Got this? All right, as long as there's a resistor. In a battery, on the other hand, of course, the whole job of the battery is to take charges from the low voltage side and put them on the high voltage side. All right, so batteries don't follow Ohm's law at all. Got this? Which is a nice little segue. Not everything follows Ohm's law. Not everything follows delta V equals IR. In fact, well, wires do because they're basically resistors. Light bulbs do because they're basically resistors too, right?
Yep.
But does the capacitor follow Ohm's law?
I'm gonna say no.
Right. Yeah. Charges don't really flow through a capacitor, do they? What do?
Build up.
They build up on one side. Yeah, and they create a voltage difference. So if you were to somehow manage to drive charges onto a capacitor, the voltage difference will build and build and build and build until you can't drive any more charges on, right? So capacitors don't work like this at all. How do capacitors work? Well, I'm going to get rid of this picture. See if I can figure out how to get rid of it. Done. Gone. We're going to talk about capacitors now. All right? I'm going to do a very simple drawing. It's going to be a battery and a capacitor. This looks like that. The instant you hook up to that capacitor to the battery, what's going to start happening?
It's going to start charging.
It's going to start charging that capacitor up, right?
Yeah.
Until when?
It's fully charged.
Till it's
Until it
what does it mean for a capacitor to be quote unquote fully charged?
full potential over the
It means that if this spot's at 12 volts here and this spot's at 0 volts here, this spot's at 0 volts and this spot's at 12. It'll charge until that's true. And then it'll stop charging because that particular battery can't push any more charges onto the capacitor. Now, if you juiced up the battery and made it a 24 volt battery, what would happen?
those numbers of double would be 24.
Yeah, you'd be able to pack twice as many charges on. Right? So if you did this with a power supply, a variable power supply, instead of a battery, if you wanted a little bit of charge on the capacitor, you just turn it a little bit on the knob. If you want a lot more charge on the capacitor, you turn up the power supply knob some more and get more voltage. Does that make sense? All right, so that's how a capacitor works. So capacitors have this interesting property. We know that the positives go like that, right? Is current actually flowing through the capacitor?
No.
No, why not?
Charge.
Because there's an air gap, right? Are charges moving through that air gap?
No.
No. But if you look at one end of the capacitor, positive charges are leaving. And if you look at the other end of the capacitor, positive charges are building up. So what we say is, yeah, we know that charges aren't actually moving through the capacitor, but we pretend like they are. Because from the point of view of the rest of the circuit, they are. Current is going from here to here, and so therefore we say current flows down through the capacitor until the capacitor is charged, and then current stops flowing. Do you guys understand that? It's like, it's not actually flowing through the capacitor, but we pretend like it is. Yes?
But eventually, wouldn't there not be any more positive charges to move?
Well, there are always positive charges to move, but eventually it's going to stop because You got so much charge built up on one side that battery can't push anymore. Okay, so to finish this up, key idea with capacitor. Capacitor is going to charge until it's charged, at which point we say the current is stopped. So basically what we can say is when you initially start charging that capacitor, it just goes like crazy, right? So when you initially start charging the capacitor, an uncharged capacitor looks like a wire. A fully charged capacitor looks like an open circuit. Why? Well, it's an open circuit because no more charge is flowing, right? All right, ponder this as you solve the capacitor network problems. Go.